A warm greetings to all. I am Karthik B from Mechanical Engineering Department, SNS College of Technology. I'm here to give a small brief note about ion carbon diagram. As you all see, this simple ion carbon diagram is placed in most of the spectral labs all over the world. Right? Okay. We all wonder that why this ion carbon phase diagram is placed in the spectral lab, and that too the spectral labs are kept in the ferrous metals dealing foundries, or in the other ways you can see the foundries which are casting ferrous metals. So the basic need is that, or the basic ideology behind keeping this keeping this ion carbon diagram in the spectral lab, it's that this ion carbon diagram gives a complete detailed about at a particular temperature and with a particular carbon percentage what type of steel is will be available. Either it's an austenitic based steel or ferritic based steel, or it's a mixture of both. So you all can easily find out at a particular percentage of carbon what type of steel is available at the particular temperature. For example, if you see at 1000 degrees Celsius, or below 730 degrees Celsius, you can see a combination of perlite and ferrite type of steel. The steel which has a combination of ferrite and perlite microstructure. At for about 1130 degrees Celsius, at 0.8% of carbon, you can see a complete austenitic microstructure. So this austenitic microstructure is mostly present in 300 series of stainless steel, and in some of the steel you can find delta microstructure at high temperatures, which is another twin of alpha ferrite. So likewise, we can easily find what type of chemical composition, or what is the major composition that is present in a particular steel at a particular carbon percentage and at a particular temperature. Not only steel, we can easily find out the cast iron grades or cast iron microstructures with this ion carbon phase diagram. So this ion carbon phase diagram contains enormous details of a iron and carbon family. So this phase diagram not only deals with the allying iron and carbon, and also deals with the addition of other allying elements to improve the mechanical property, metallurgical property, and chemical property of a particular alloy. So for example, if we take at a 0.8% of steel, you have a austenite microstructure. So this austenite microstructure, you can easily say the 300 series of stainless steel has this austenitic microstructure. But we all wonder is that you can see the red color, which is austenite, this phase diagram has their loop up to 730 degrees Celsius, but we are finding this austenitic stainless steel at the room temperature without any deformation or degrading of any of their properties. It's a simple mechanism is behind. The thing is that they are using austenitic stabilizers to stabilize this austenite at the room temperature. So you can attain the austenitic properties advantages at the room temperature itself, like high strength, high corrosion resistance. And another part we can say, for example, if you take a stainless steel, we all say it's non-corroding, or it has high corrosion resistance. The basic thing behind this is they are using chromium with the iron carbon, chromium and nickel with iron and carbon. So their corrosion resistance increases due to this elements. So these elements not only enhance the properties and also act as a stabilizers for a particular phases that can be available at the room temperature. Okay, thank you.